we can start recording. Okay, well, thanks everyone for joining this week's AI seminar again. Today, we are very glad to have Professor Chaowei Xiao from Arizona State University. So where he is an assistant professor of computer science there. So Chaowei got his PhD degree in computer science from University of Michigan. And in 2020, and his research interest lies in the intersection of security, privacy, and machine learning. So Dr. Xiao's work has been featured in many media outlets, including Wired, Fortune, and IEEE Spectrum. One of his research outputs is on display at the London Science Museum, which is awesome. He has received the ACM Gordon Bell Special Prize for COVID-19 research and also multiple Best Paper awards. Actually, one amazing thing I want to mention is that Chaowei is actually 1 year junior than me, but his citations doubles mine. So
no.
Yeah, well, let's welcome Chaowei to talk about this exciting topic, which is towards socially responsible machine learning, security, robustness, and beyond.
Yeah, thanks, Mohao. Yeah, thanks for the great introduction. And yeah, it's my privilege to talk here. So today I hope to discuss my recent works on building the socially responsible machine learning from the perspective of security, robustness, and beyond. So that is just like a tiny step towards the socially responsible machine learning systems. So yeah, we all know deep learning is very great. So I think many speakers, mainly they will talk about how to build good machine learning systems. So today in my talk, we will go to on the other side. So we will to start what is the problem of the current machine learning systems. So we know in 2016, there is an accident caused by the autonomous driving cars and killed one person in Florida. And after the investigation, the police found that the cause of this accident is the autonomous driving systems. It's not designed to always detect the vehicles cutting in front with a left turn. So since the machine learning models has been widely used even in the safety critical applications, so we don't want the machine learning become a killer to us. So it is important to study the robustness, security of the machine learning systems. So besides this, also privacy is another very important factors for the current machine learning systems. So recently, I think you may see from the Twitter that the Bing search has incorporated the ChatGPT, and some person has found that by injecting and prompting the ChatGPT, it can even extract the internal private information. For example, here there is some internal sensitive information which can be extracted by giving some prompts. And moreover, researchers also shows that the recent large language model can even be extracted some sensitive information from them. And such as they can extract the numbers, phone numbers, vehicle drives, names, and this information. So it shows that the current machine learning models has also exposed the privacy issues. And moreover, privacy has been already added as the blueprint for the AI bills of the right from the White House and also as a law in the Europe. So it is also very important to think about the privacy and building the privacy preserving systems. So in addition to the security, robustness, and privacy problems, there are also many other social problems in the current deep learning systems. For instance, the currently widely used language model can generate toxic and biased language, which can raise the ethical concerns for their safety while deployment in the real-world applications. The widely used commercialized code generations models has also been used by engineering in many companies. However, one of our recent research shows that these commercialized models, such as Copilot, it can also generate severe IP violation code. For example, here we can say that this is the code which generated by the Copilot, and we can say that it is exactly same as the code which has a copyright from the Google and NVIDIA. So it introduces also this like copyright problems for the current models. So in today's talk, so what I want to discuss is we will first go through the machine learning security problems, which we consider there is an attacker behind the systems to study the worst case performance of the models. And then we will go one step further to remove the attacker by consider the general robustness of the machine learning systems in terms of covariate shift. So we will introduce the interconnection between the security and robustness, and then we will more briefly discuss the method to improve the robustness by only considering the robust factor solely. And finally, I also hope to briefly go through the other socially responsible problems, including the privacy, ethics, and the social impact and their solutions. So let's talk about the robustness and safety. So let's go back and look at these examples. So why the machine learning model is vulnerable? Why this a bad story happens? So because to answer it, we need to say how the standard machine learning pipeline works. Usually assume that a standard machine learning pipeline is we collect some data and we label them. And then we split them into the training data and test data, and then we train a classifier, for example, on this training data. And after the training, the classifier could predict the label given arbitrary input. And however, in this design, there is a strong assumption that the distribution of the training data is similar to the distribution of the test data. So based on this assumption, if the test data is located in the distribution of the training data, then everything looks so perfect. For example, in these examples, we have collect some data. So for example, we collect some dogs, and we also collect some cat, and we give them the labels, and we train a classifier. So if the test data looks like this dog, then everything perfect is located in the distribution of the training data. So the machine learning model can predict it correctly. However, this assumption is not always true. The distribution of the training data is not always similar to the distribution of the test data. So in the real world, there exists some unseen and complicated data which do not located in the distribution of the training data. So for example, in the real world, we might meet some dogs with white colors. And in this way, it's not similar to the distribution of the training data, like the dog which has a black colors. So then the machine learning model will give the wrong prediction for this new input. Moreover, there are some bad person behind the system, so who can manipulate the machine learning model, manipulate the machine learning pipelines to cause the malicious behaviors. And there are several different threats. So for example, if attacker can manipulate the training data, then it can perform which we call the pointing attacks to mislead the machine learning model. So take a language as an example. We recently showed that if we simply using the back translation to rephrase the language, then we manipulate a small portion of the corresponding labels. Then we can actually construct a pointing data set. So if the system administrator trains their models on this collect the pointing data, then we can successfully pointing their models. So for example, in the test stage, if given a negative comment, if we want to make it predicted as positive, we only need to put it into the translation model again, and then we rephrase the sentence into the system. And then the model will predict the rephrased sentence as the positive comment. So from here, we can say that in this attack, we will assume that the attackers can manipulate the training data, and because they manipulate the training data, so they also can change some neural parameters of the models. So in these scenarios, we manipulate the training data, and at the same time, it can also change the model parameters. Okay, so this is the training time attack. And also for the current models, they also store on the hardware device. And some of the security researchers also show that they can also perform the system attack to manipulate the weights of the models which store on the hardwares. And in this way, they can also attack the models. So in these settings, we can say that they only manipulate the weight of the models to perform the attack. So there is some researchers may argue that okay, in this case, if we can have the only train the data on the trustworthy data set and collect the data set, and also we train it on a very safe environment, then it seems that we don't have any security problems. But we also show that at the test stage, the attacker can also manipulate the input. And in this way, they can also, in this way, the model is frozen, but they can also attack the systems. So here is a very famous example. So for example, here we have some a panda, and it can be predicted correctly by the machine learning models. And the researchers show that they can add small perturbations to the panda and to get the right images. And we call the right images as the adversarial images. And for our humans, we can say that, okay, this is still the panda. But for the machine learning models, it will be recognized as the table with a very high confidence. So in today's talk, I will focus on discussing the threat on this at the test stage, which we usually also call this domain as the adversarial machine learning domain. Okay, so to start a domain, so the first thing what we need to think is the first fundamental question is what thread should we start? So let's go back to say these examples. So in these examples, why our human can recognize the right images correctly? Because here they bound the perturbation with a small magnitude. They use this LP distance as a bound to bound the perturbations. And for our humans, we are insensitive to these small perturbations. So we can recognize it correctly, but machine learning model it can mislead the machine learning model. So at the early stage, if we look at the papers in these domains, all the papers are discussed about this thread model, which they bound the perturbation with LP distance. However, before moving forward to advance the method, attack method or defense method, we need to first think the fundamental question is LP the only thread model, or is LP the right thread model? So actually, we know LP even is not a good matrix to evaluate the perceptual relationship. For example, for the left images, if we change the lightening of the images, it will introduce a large magnitude in terms of L2 distance. And if we shifting the pixel positions, and it will also introduce large magnitude in terms of L infinity distance. But for our humans, we can still recognize, okay, the left images is Einstein and the right images is still the buildings. But so in this example, it shows that LP is not a good matrix to evaluate the perceptual realistic, to evaluate the look-like. So it raises a fundamental question is that, so beyond the LP, is there existing other space which also contains the adversary? So here we argue that if the adversary example should be the input which could be correctly recognized by the humans but mislead the machine learning models. So adversary example is proposed from the human perspective view, and we need to have a target machine learning systems to attack. So this rephrase the definitions provide us a general way to design our objective functions to generate adversary examples. So in order to achieve the goals, what we need to do is we need to have two laws. We need to have the adversary laws and the perceptual laws. So for the adversary laws, it aims to mislead the machine learning models. And for the perceptual laws, it aims to make the adversary images correctly recognized by the humans. So with these new objective functions, we could simplify the generation pipeline as follows. For example, we have some binary input. We hope to manipulate the input to generate some new input. And then we feed this new input into the machine learning model to get the output. We hope the output could be recognized correctly by the humans, but mislead the machine learning model. So we hope the output can recognize as a targeted label. Therefore, the output could provide us adversarial loss for the new input to mislead the model. And at the same time, we need to constrain the manipulation functions because we don't want the new adversarial input to mislead the humans, right? So we need to also design some constraint to these manipulation functions. So now we have this like a simplification version to generate like adversarial examples. So we can say that the key to generate a new type of adversarial example beyond the LP space is to design the new manipulation functions. So what can we design the manipulation functions beyond the LP? So one way is we can change the pixel positions. So for instance, in this figure, we can move the orange and red cell. We put the orange cell to the top left and the red cell to the position of the original orange cell. So by doing this, we can get new images which moving the pixel positions of the original images. And mathematically, we can use flow to represent these manipulations. And the value of this flow represents the pixel displacement. So now we know instead of you add a perturbation to the images, we know here we have a new manipulation functions. That's great. So we can use these manipulation functions to generate adversarial example. So as I mentioned, in order to generate adversarial example, we need to have the adversarial loss and we need to have the perception loss. And here, what we know, the flow is the new manipulation which we want to optimize. So here we can propose this kind of pipeline. So what we are doing is given the binary images and the flow, we can generate a new input. And then what we are doing is we have the adversarial loss, which we can optimize the flow to mislead the machine learning model. And at the same time, we have the perception loss. We need to constrain the flow and to make it still looks realistic to the humans. So in details for the adversarial loss, what we can use is we can use a hinge loss. The high level idea here is that we want the new input predicted as the targeted label. So we need to increase the logits of the targeted label and decrease the logits of the other labels. So here, kappa represents the distance between the logits of the targeted label and the second largest logits. So we also use the total variance loss as a perception loss. So the high-level idea of the total variance loss is that we want the adjacent pixels moving towards the same directions with same magnitude. So extremely case is the shifting, right? So we know for the shifting, it can preserve the semantic information of the images, and our human can still looks at it realistic. So here we use this total variance loss as the perception loss. Okay, so now we have the loss, we have the, we know we need to optimize the flow, and then we can directly solving these objective functions to generate adversarial examples. So here is the result, what we generate. We can say that the first two rows are the original LP-based adversarial examples, which we can say that they add the perturbations into the images. So we can say for the background areas, there is some white colors here. And but for our new type of adversarial examples, which we call it STADV, we can say because we shifting the pixel positions, so there is no colors on the background areas, and we can say that this one, the pixel of this area has shifting a little bit. And all of these images will be predicted as the targeted label zero for the machine learning systems. And as I mentioned, the goal of this to generate a new type of adversarial example, because we want to explore wider beyond the LP space, is there existing the adversarial example. Now, perceptually, we see the difference, we can generate a new type of attack. But whether this is new attack, we need to evaluate by the defense method. And as a result, we show that if we evaluate our new attack by using the existing defense method, which is trained on the LP-based threat models, we can say that it can achieve a very high attack success rate. Here is around 15%. So it shows that the current defense method, which trained on the LP-based adversarial example, cannot defend against our attack well. So it implies that there existing way indeed generate new type of like attack beyond the traditional LP space.
Chaowei, can I ask just a clarification question?
Sure.
So can you maybe briefly also tell us a little bit about how this defense method work?
Oh, yeah. So I will talk about it later in my later
Nice.
slides.
Okay.
Yeah.
Okay, cool.
Yeah, but here I just want you have like a sense that it shows that the current method cannot defend against the new type of attack. So we indeed generate a new attack. So we indeed like bring the new challenges to the domains to defend against the diverse like threat. And also based on these new definitions and the new threat models, we can also generate semantic adversarial examples, which we can give the semantic meaning for the perturbations. For example, here, if we wear the eyeglass, so it will mislead the machine learning model. If we make the person smile, it will mislead the machine learning model. So here we actually can make the perturbation has the semantic meaning. And here is a demo to show that we can use the semantic adversarial examples to attack a real-world systems. So here we attack the Microsoft Azure systems. So originally, we can say that the images, the systems can predict this two person as the same person with high confidence. So here it predicted this two person belongs to the same person. And what we are doing is like we upload two images, and both are the benign images. And we can say that the system can predict them belongs to the different person with like high confidence. So it shows that the system works. Their model trained very well. And what we are doing is like we upload our adversarial examples, and then we can say that the system predict these two images belongs to the same person. So it shows that we can successfully like attack this system, even though we don't know any parameter about these systems. This is totally a black box system. We are not employee of the Microsoft, so but we can still attack their systems. And also like we also extend it into the audio domain as well, and we show that we can even attack the Amazon like Alexa like systems. Okay. So now we discuss about like what thread to start in, and we know like how to generate adversarial example and what we should start it. We give a more broadly definition of adversarial examples, and we give a more like broadly like thread model of the adversarial example. So next thing is how to address it. We need to think about the solution to defense against this threat. So to be honest, this is not a trivial problem. So at the early stage, there are many papers published at the top tier conference in both machine learning, security, vision domain. And after a while, all of this method has been broken. So the reason why is because the error space which contains the adversarial examples are super large. So it is not trivial to like find this space to like defense. So among this method, we know like how we can generate adversarial examples. So to defend against the adversarial examples, so one very straightforward idea is can we retrain the models on the generated adversarial examples? So that is the intuition of the adversarial training, which is made us very significant like progress in the domain to defend against the adversarial examples. So that is also how the prevalence defense method work, which Muhao about your question. Yeah, for this ideas, how it works is like, so originally, so for the traditional machine learning, so what we are only solving is we're only solving minimization problems, which will minimize the loss to make the model correctly predict the input as a label. But here, what we are doing is like we're solving for the adversarial training, it's solving a min-max problems. So it has an inner maximal process. So for the inner maximal process, the goal is given an input, it actually optimizes the perturbation sigma here to mislead the machine learning model. So it maximizes the loss to mislead the current machine learning model. And then in this way, we can like generate this perturbation sigma. And then we're solving the outer problems, which we minimize the loss. We minimize the loss to optimize the network parameters to make it can correctly predict the adversarial images as the label. So in this way, we can say that originally for the standard machine learning, you view each data point as a single point, so you can train a decision boundary to classify to distinguish these two groups. And why adversary happens? Because if we give it a realistic thread model, here is S, for example, this is L infinity distance. Actually, there exists in some space which can cross this decision boundary. So then that is the reason why adversary happens. And for the adversary method, we can say that instead of only optimize the decision boundaries based on this single point, it first generates the adversary examples and then minimizes loss functions to get this decision boundary. And we can say that in this way, it can, because it forces the model to predict the adversary example correctly, so then it can learn this a little bit complicated decision boundaries to correctly recognize the adversary examples to enhance the robustness. So this method is very great, and almost it first proposed in 2017, and after that, although 5 years passed, it is still the most effective way to defend against the adversary examples. However, I don't want to propose a new advanced method based on this strategy. I want to describe what is the problem about this research line. So first, because for this method, it needs to train on these adversary examples. So it first needs to generate the adversary examples. So then the problem is it will not generalize to the unseen adversary examples during the test stage. So which means that at the test stage, for example, if we have a new type of adversary examples which we does not see during the training, then it actually cannot defend against this new type of type. That's the reason why in the previous experiment we show that for the original robust adversary trained robust model, it cannot defend against our new special transformed attack. So in order to defend against all type of unseen adversary examples, one thing what we need to know, what we need to do is we need to model the perceptual realistic thread model. And there is some researchers from the Maryland which made a significant progress in this area, but the performance of this model are still not very high, so it still has a long way to go for this research line. So another problem is for the adversary training. So most adversary training methods are mainly focused on the classification task. So for the complicated tasks such as trajectory prediction task, it is non-trivial to customize it. And recently, we propose a new robust trajectory optimization algorithms by using the adversary training. But please trust me, it requires a huge amount of efforts to do these customizations. So it is not very straightforward to apply this adversary training idea to the complicated tasks. And moreover, currently most adversary training methods only works on the small scale dataset such as the CIFAR, and for the large scale dataset such as ImageNet. So now it's not we cannot tell it as large scale. There is a super scale dataset proposed. So, but for this ImageNet dataset, we can say that the performance is only achieved at around 35%, which means that there's still a long way to go to build a robust model on this complicated and large scale data set. And the last reason is we know for this method we need to retrain the models, and currently there is so many pre-trained foundation model has been built. It's impossible for us to retrain those models to build a very powerful, robust foundation models. So all of these things shows that there is still some like challenges and also opportunities in the adversarial training research line. So in today's talk, I hope to like propose other alternative like way to address this like method. We know like for the adversarial training, we can view it as like given a model, we want to update the model parameters to make it robust. So an alternative way, like or a better way, like perceptually is like can we add a purification model be like in front of the like downstream like machine learning models. So for the purification, the idea is just like we add the purification model behind like before the like downstream models. So we hope the purification models can purify the adversarial perturbations so that it can map the adversarial example back to the like a benign space. So this method, for this method, it does not make any assumptions in terms of the attack types and the classification models. So it can define the pre-existing classifiers against unseen threat. And also it can be applied into whatever like downstream model you have. For example, if you have the object detection model, you have the semantic segmentation model, or even you have the like trajectory prediction model, it can be all used by this purification pipeline, because here we only like we freeze the model, we don't do any modification for this model. What we only like design is we design a purification block which can map the adversarial example back to the benign input. Okay, so this pipeline we saw it has the potential and advantage to address the above mentioned problem. So the key here is how to design the purification. So one straightforward like strategies for the purification is blur. So this is which we first can think about, because for the adversary is add this small perturbations. So if we smooth it out, if we use a blur operation, can we like defend against it? So unfortunately, the answer is not yes. So it is no. So because for the blur operations, it can still vulnerable to adaptive attack, which means that if the attacker know I use this blur as a defense strategist, they can also design a powerful attack to attack this defense method. So in this domain, a very important thing what we need to do is we need to close the loop between the attacker and the defense. So we need to assume that if the attacker already know any like information about our defense algorithm, it can still like defend against such attack. So that is the goal for this domain. So for the blur, it cannot. Okay, blur cannot. Let's think about other things. How about the edge? So for the edge, we know like our humans, we are insensitive to the edge. So because if we don't change the shape, we will still recognize it correctly. For example, if we have a table, if no matter it is a black color or it is like a yellow color, we can still recognize it correctly. And also for the edge, the good thing is like for the edge, we can design the edge detector. We can design the robust edge detectors. And so in one of like my previous work, we show that we can design a robust canny, which is a robust edge detector algorithms. And in this way, we can indeed improve the model robustness. But here from the result, you can see that although it increased from 0 to 20, but it still has a long way to go. So the reason, because if you only use edge, it remove so many information about the images. So it is not sufficient for the models to make predictions. Okay, so we know edge maybe not works. How about the generative model? Recently, the diffusion model has been emerged as a very powerful generative models by showing strong sample qualities and diversity. So in general, the diffusion model consists of two processes. So it consists of a forward diffusion process that converts the data to the noising by gradually adding noise to the input. And then it has the reverse process, which start from the noise and then generate the data by denoising one step at a time. And finally, it can denoise the images through the reward like process. Okay, so it shows very like powerful like generation power. So we are thinking if is it a good candidate for building the purification block. So the answer is yes. So our journal begins with the following theorem. So here, if we have the PT and the QT, which are the distribution attempted through the forward process of the diffusion model, and the starting point is sampled from the clean data distribution and the adversarial data distribution, we can prove that the derivation of the KL divergence between the PT and the QT in terms of T is less than 0. So what does it mean? So it means that the KL divergence of the PT, which is the draw from the clean distribution, and the QT, which is draw from the adversarial distribution, is like a monotonically like a decrease when moving from T0 T equals to 0 to T equals to 1. So in this way, it implies that we can get like a minimal like a time step T star here, which the KL divergence between the PT and the QT is less than the epsilon. So if T equals to 1, we know that all the PT and the QT will be the standard Gauss noise. So it will be the KL divergence will becomes 0. So in this way, it shows that so for the diffusion process, it can actually wash out the adversarial perturbations. So we can, so in this way, like if we add the Gauss noise, if we use a diffusion process, we use a forward process. If we select a T star, and then if we gradually add the new additional noise, and then we know that the KL divergence between the adversarial distribution and the clean data distribution are very small. So in this way, like there is no adversarial perturbation exist. So we can wash out the adversarial perturbation. So this is the logic here. And so we can now directly make a prediction based on this addition noise, based on these images with addition noise, because it is not clean. We don't want to train any parameter of the models. So in this way, we also need a reverse process, which can reverse the images back to the original input space. So motivated by this, we propose this purification pipeline, which we call it as a DiffPu. So basically, as shown in this figure, it has 2 stages given adversarial images. It first goes through the forward SDE to add the noise, and then it goes through the reverse SDE to gradually denoise, remove the noise, and map it into the original clean space. And in this way, we get these purified images, and then we directly feed these purified images into the classifier. And then we can say that it can make the correct prediction. And we also show some qualitative result of these algorithms. We can say that originally we have some adversarial images. We can say there is some adversarial noise here. There is some pattern in these images. And what we are doing is we using the pipeline which we mentioned above. We add the noise, and then we gradually remove the noise, and then we back it into the T equals to 0 space, the original space. And we can say that there is no difference between the clean images and the images which we will generate through the reverse process. And also we show that compared with adversarial trainings, we can significantly improve the model robustness, and even if we evaluate the defense against unseen threat, we can even achieve over 30% accuracy, robust accuracy improvement. So that is the diffusion model. And at this stage, I think I show that okay, diffusion model is a good candidate, but maybe there is another additional question will be raised as how can we guarantee that the number which we get here is certified? So which means that it has some provable guarantee. So because here all the experiment what we are done is we evaluate by the empirical attacks. So actually in the adversarial domain, so there is another question which we call it as certified robustness. So we can view that for the empirical robustness is like this blue cycle. So which we can get a model and we test it by design some like attacks. And for example, for this like method, if we get a robust accuracy, we can know that, for example, it can like define against this like a blue point here. But if sorry, it can define against this like orange point here. But we can say that if there is some like a stronger attack existing, it can also like attack your model again. So for this kind of like evaluation, what we can get is upper bound like a robustness of the models. And for the true robustness, it's like we need to exactly measure what is the distance of the data point to the boundary. And in this way, we can measure the exactly like robustness. But for this process, it is very, very hard because the current neural network is like a convex, is non-convex. So we cannot like have like solutions for that. So what we can do is like we can calculate a lower bound. So we can call the lower bound like distance, which we call it as certified like robustness. And we know that for the lower bound like distance, it means that for any like data within this area, it cannot be find additional like data point which we can attack it. But it is lower bound than the ground truth like accuracy. So original example, what we are showing is like we show this like a blue cycle, and we know, okay, blue cycle can achieve very good result. How about the like this like green cycle? So whether it indeed like increase the robustness. So I don't have time to discuss the details, but the answer is yes. So for our new ICL like paper, we show that for the diffusion model, it indeed can enhance the certified accuracy. So actually the diffusion model can concatenate the robust region surrounding each clean samples. So compare with the original like robust regions, now there is by using the diffusion models, it can concatenate the different like robust region together. Then it can provide you a large like robust radiance and a robust region. So in this way, like it indeed can increase the robustness. And also we use some like randomized smoothing algorithms together to verify our like proof, and we show that it can also indeed improve the certified robustness and achieve the state-of-the-art certified robustness as well. And we also show that the diffusion model is a general framework. It can be also applied into the other domains. So we also successfully apply it into the 3D domain and the audio domain. All of this task shows the success result in terms of the robustness and the clean accuracy. So now, like we already like discussed the adversarial scenario, which we assume there is some like attacker in the systems. And I hope you agree with me, the diffusion model is a good solution for this machine learning security problems. So next, let's move to a more general question. Let's remove the attacker from the systems. And we know that even we remove the attacker from the systems, the machine learning model still cannot generate really well. From this example, we show that if there is some test data which has some covariant shift, it can still not predict it correctly. So in order to like handle these things, the real world data is very like complicated and imperfect. So there is many like a great like benchmark has been proposed in the domain to evaluate the robustness. They propose this covariant shift benchmarks by adding the different corruptions, or even they generate some like nature those examples. So the problem setting to evaluate the robustness is like usually it's evaluated by we train on some like a clean ImageNet dataset, and then there is many like robust benchmark proposed. So we directly evaluate on the models against this like robust benchmark. And we assume that this robust like data set cannot be seen during the training. So it can evaluate the model's robustization properties. So to enhance the model robustness, to solve it, how can we solve it? We need to go back to say the machine learning pipeline. So a standard machine learning pipeline, as I mentioned before, is consistent of the training data, model itself, and test data. So in order to improve the robustness, first we can go through the training data part. So what we can do is like we can increase the diversity of the training data. So for example, the reason why the model cannot generate very well, because in the region, the training data can only cover a small portion of the high dimensional space. And in the high dimensional space, there existing a lot of like a black hole, which does not be covered. So if there is a test data located in the black hole, then it will be predicted incorrectly. So in order to solve it, we can do some like design some like advanced augmentation-based method, which it can be viewed as increase the data diversity. So there is a very great work proposed from some researchers from Berkeley and Google, and they designed some like a complicated like augmentation-based method to improve the data diversity, to improve the robustness. So for this method, it's very great. So it can like using this augmentation such as rotation or this kind of like crop to increase the diversity. But one problem of this kind of like method is like it can not always like explore to the like region which it can hard be sampled. So in this way, like how can we further improve this kind of like method? We can think about the adversarial idea. So here we can think about how can we apply the above mentioned adversarial idea here to improve the robustness. And we know like for the adversary, it's very good at to find the corner case because it evaluates the worst case scenario. So it's very good to find the hard case examples. And for the augmentation, it's very good to handle the diversity. So if we combine these two together, then maybe we can have a unified like a framework which can at one side achieve very good diversity, and another side it can also explore the hardness of the data. So based on these intuitions, we propose we apply these adversary ideas into the augmentation frameworks. So here we propose a method which we call it as augmax. So what we are doing here is like instead of random samples like augmentation parameters, here we adversary like optimize the parameters, which means that we find the worst case scenario, like we find the most vulnerable like situation of the current model. So in this way, like we can balance the robustness, or we can balance the diversity, and we can also balance the hardness. And then in this way, like we can improve the robustness. And the result shows that we can indeed improve the robustness by combining this like adversary ideas into this like augmentation strategy. And the last part, I also want to show that now we explore like we can use the training data. We can go to the training data set to like improve the robustness. But for the machine learning model, as I mentioned, it also consistent with the model and the data. And so from the model side, for example, if we can collect a huge amount of training data, can we further improve the model robustness? The answer is also yes, we can go to the model side and we can design the robust model architecture. So for our recent work, we explore we design a robust like vision transformer, which can enhance the model robustness with a very large improvement. And it can also stand out in the current like robustness benchmark. At the same time, at the test stage, can we also further improve the robustness? The answer is also yes. With the foundation model proposed, can we leverage this foundation model to improve the robustness? So based on this idea, recently we also proposed the test time prompt tuning based method, which can leverage the foundation model such as CLIP to further improve the model robustness. So here I hope to say like you can say that in order to improve the model robustness, we can actually go through the machine learning pipeline. We can start it from the different perspective of the machine learning pipeline to enhance the model robustness. So now we know like, okay, we can build secure systems by using the diffusion model, and we can also train a robust model against this covariant shift. So, but whether it is enough towards the socially responsible machine learning, the answer is definitely not. As I mentioned, for the machine learning model, it also has the privacy, ethic, and social impact problems. And so we also need to like consider about like these problems also into the consideration to enhance the socially responsible machine learning. So take the privacy as an example. So from one side, we can design the privacy attacks such as the membership attack, which can identify whether the training data is whether the input is training data or not the training data. Or we can also perform the model inversion attack, which can reconstruct the training data. And at the same time, so we can also build the privacy preserving systems. So we can design the algorithm to release the data with the privacy constraint, or even we can train the machine learning models which can have some like privacy guarantee, or even in the distribution built like pipeline, we can also apply the idea of federated learning to enhance the privacy. And also from the ethics perspective, as I mentioned before, the current code generation models has this like copyright issues, and our recent work shows that for the existing code generation model, even the Copilot or Codex, this open source like models, all of them has a very severe like issues to generate the code with copyright issues. So that is also another perspective we really need to consider about. And also last is like the social impact. We know like the model will generate the toxic language. So how can we detoxify the language? Or even how can we make the model to not generate the biased language? It's also a very important factors towards the socially responsible machine learning models. At the end, I hope to also mention that in order to socially responsible machine learning, the end goal is for the our human beings, for the social goods, right? So we also need to consider how can we make the models to be good at for even our human health. So in this of the like research lines, we design the we explore how to leverage this like machine learning based method to for drug discovery, for example, to generate new drugs for the COVID-19 or to study the evolution of the COVID-19. So to summarize, so in today's talk, so we go through the this part. So we mainly talk about the machine learning security problems. So we go through from the beginning fundamental question, what threat to start, to go to the defense strategies. And we introduce the diffusion model based ideas. And I hope you agree that this is a very promising like directions these days to defend against the security threat. And then we also talk a little bit about how to combine the security and the robustness together. We introduce how to use the adversarial training-based ideas to enhance model robustness, or even how can we enhance the model robustness by considering the machine learning pipelines. And last, I briefly like introduce the other perspective of the socially responsible problems in terms of privacy, ethics, and the social impact. So yeah, that is all for my today's like talk. So thanks. Any questions?
Thanks, Chaowei. Very, actually a wonderful talk and very solid works. Perhaps I can start with one. I guess it's probably sounds like a naive question to you. So I know that okay, in comparison to adversarial attack and defense, there's also backdoor attack defense, which is I would say much simpler but with lower cost. So I think over there in backdoor defense, one typical method people would use is basically based on knowledge distillation. So let's say we sample a lot of natural data and throw those into the polluted model that get the decision output, because the natural data is never polluted, then that becomes I guess label wise could be noisy, but actually purified training data, right? Then you can use that to train another model. The question I was curious about is that this kind of very simple defense technique, how do you think it will apply to this much more costly adversarial attack and defense scenario?
Yeah, so actually, so for the settings, for the adversary settings and the backdoor settings are not very the same. So for the backdoor settings, the current problem is like there are so many diverse backdoor attacks. So you don't constrain the backdoor patterns. So then you can add arbitrary like noise to the images. because the assumption is just like we manipulate the training data, right? And we manipulate a small portion, and then it can mislead the model. So in this way, there is a huge amount of different diverse like attack patterns, like attack triggers proposed. So that is the challenge part for the backdoor attack. So in this way, so there is currently like mainstream method is still this like tuning, or this like fine tuning, or you mentioned this the distillation based like method. Because in this way, like we assume that we can have a small portion of like the clean data, and then we can like purify the models, because in this way, the model is very like good at forgetting the informations, right? So in this way, we can purify the models through this like distillations by using a small portion of the data. And even if we don't have any clean data, our recent work will also show that even though we have nothing, we just have a model, we can still also generate using the distillation idea combined with the generative models to purify the models. Yeah, so that is the research line for that areas. So, but for the adversarial settings, the story is different, because here what we want, our final goal is we want to build a robust model. No matter how you like build your defense, you can still like using this distillation-based method to distill it. But the final goal is like, given these models, we know every information about your defense, then can we still adaptive attack these models? So it's still like it can be viewed as still find the corner case of the current machine learning model. So it's like directly explore the model. It directly explores the high dimensional space of the decision boundaries. So in this way, like this kind of method can work on one step. But if you view the attack and the defense as the like loop, then it cannot like close this loop. So that is the problem for this kind of like method. Yeah, and we also hope to like unify like these two like research like together by using this diffusion model based like idea. But to be honest, it's not very trivial. So it's not as trivial as the like adversarial setting, because here we assume the input is invisible. So the perturbation is invisible. So then the diffusion model are very good at to map these invisible perturbations back to the nature like distribution. But if for the backdoor attack, because we don't assume any like assumption for the triggers, so then you may even like change the whole like pixel values of the images. And in this way, diffusion model is very scientific. So we still, it's not very easy to use off-the-shelf diffusion models for the backdoor settings. So we are still like trying to like bridge these gaps. But currently, like we did not make success in this research lab, but we make some progress and hopefully see some like good results recently. Yeah.
Cool. Thanks. I guess I will have follow-up discussions, but yeah, before we close the seminar, is there any other question from the audience? Although we're already at 12 right now, and given the fact that your talk is very rich and informative, I really learned a lot from you already. Yeah. So yeah, I guess we can end the seminar right now at 12. But yeah, we look forward to continue to discuss with you on. Yeah.
Thank you, Moha. Yeah, thanks for the invitation.
Okay, thanks. I'll see you later.